You're watching this video now, meaning there's a server somewhere in YouTube's backend that serves it to your browser or mobile app. Without disrespecting you or me, this server has probably got a few other tasks than us. In the old days, and by old I mean 10 to 20 years ago, companies had huge servers in their basement with lots of guilfoils physically maintaining them and installing the backend applications. But over time, these started conflicting with each other, requiring different versions of local utilities, sharing disk space and memory, overwriting each other's data. The tech world noticed the problem and tried creating separation. At first with something called virtual machines, and then, and I'm making this long story quite short, containers emerged, based on a Linux concept that mainly sysadmins are aware of called namespaces. Now, these allow for a very efficient way of creating isolation and allocating resources to different processes without hurting their neighbors. Back to you watching this video, the backend server is probably a huge machine with many different containers running many different applications and the replicas so that you can enjoy this video while your friends at work are enjoying other content. But that's not all containers can do. They're great for replicating applications environments, eliminating the most hateful sentence by DevOps engineers worldwide.
But it works great on my machine.
Moreover, containers can run local utilities without installing anything. They can safely connect an entire production environment on your desktop computer with minimal resources, making developers' life so much easier if only they know how to make the use of that power.
It makes me feel useful and powerful.
And that's what we're covering today. Working with containers for the past 11 years, from a junior DevOps to a cloud architect, I'm going to take you from absolute beginner to knowing the essentials of containers and everything you need to know around them. You probably think of containers as synonymous with Docker, but they really aren't. Throughout this video, I'm going to work with Podman, which is an open source alternative, but every single command I run here can be identically replaced with Docker. So don't stress it. Install either or both. There's no difference as for this session, and I made a video covering all about it up here. Whatever you choose, make sure it runs. If you go for Podman like I did, it needs to have a machine, so run podman machine start, and if all goes well, it'll say it started successfully, and you can confirm that by running podman machine ls. The first command you'd want to learn for containers is ps. It stands for running processes. Note that these are not identical, and I'm only running both to stress that containers run with Podman will not reflect on the Docker list and vice versa. So pick your poison and go with that. I listed my reasoning before and in a dedicated video, but here's one factor. Docker requires a bunch of processes running in the background while Podman doesn't. It's daemonless and has proved to be lighter on my system. To get started, let's run our first container. Podman run and a container name is the basic command for running local containers. Let's get the famous hello world from Podman. If you run podman info, you'll get a list of important information about the host, the machines, and other paths. Amongst we have the configured remote registries. Most of the containers CLI defer to Docker Hub, and this is the configured search registry so that when we search for containers, it'll start there. Let's pull BusyBox, which goes to search it on Docker.io with the default tag latest. Tags conventionally listed after the image's name and path, separated by colon. If they aren't mentioned, latest is inferred, but it's a good practice to avoid latest tags as these can change. Most official images have many versions, like lighter options, versions based on Alpine Linux, slim options, etc. You'll note a bunch of hashes being pulled. These are the container layers. Without getting into too much detail, every container image is built from layers. This improves caching, storage, and improves pulling and pushing times if built correctly. Imagine having to only pull the new application updates and not its operating system and dependencies if these haven't changed. Before we dive in, let me tell you about today's sponsor, Twingate, the smart way to secure your remote access. You know how traditional VPNs are like having a single fortress gate? Once someone's in, they can wander anywhere. Well, Twingate flips this model on its head with zero trust security. Think of it as a modern city, where every district requires its own access path. Much safer, right? But here's what's really cool, especially for you developers out there. Twingate now seamlessly integrates with Kubernetes, so instead of bouncing between engineering and IT teams, you can configure secure access right in your YAML files. It's all part of the regular engineering flow, no context switching needed. Setup takes minutes, not days, and works across all of your devices. Plus, you get enterprise-grade security without the enterprise-grade headaches. Whether you're managing a remote team or running complex Kubernetes deployments, Twingate handles the security heavy lifting and you can focus on what really matters, building great software. Ready to level up your remote access security? Head over to twingate.com for a free trial and see why thousands of teams trust Twingate with their secure access needs. About that BusyBox I mentioned earlier, working with containers, you're going to hear about it a lot. It's an incredibly small container, which actually packs many Linux utilities into one binary that runs in a container, making it Unix-like environment with less than 5 megabytes in size. Want to know how I can tell the size of the image? Images subcommand will list existing container images, amongst of which BusyBox with a size out of this world. Simply running BusyBox doesn't do much. There is no service or process to run, so the container runs and shuts down immediately. Let's tell it to run something by adding a command. We'll use the echo utility to print something to the screen. By default, containers share their std output stream, and there's the output. Checking for running containers again shows an empty list as expected. What if we want to use the container and explore it from within without it exiting immediately? One of the ways to achieve that is by running the container with an interactive shell flag and adding sh as the command to run, which will create a shell for us within it. Inside the container, we can explore the environment, install utilities, and make changes. Let's demonstrate an extreme example of such a change, and please kids, don't try this at home. We'll delete the /bin directory to eliminate all the binaries on the container. None of the utilities work now. I mean, even clearing the screen is not an option anymore, so let's exit the container, run it again, and there we are, with a fresh, identical environment started from scratch with everything properly working. If you're interested in listing all the containers in the system, even those who aren't running, ps-a will pop a list of all of them. Adding a -q for quiet and filtering status exited will export a list of IDs for all containers stopped, which can be extremely useful for cleaning out all garbage dead containers by wrapping them in a subshell and adding the rm command beforehand. But recently, Docker and Podman following added the container prune command that does the same with 10% the hassle, so let's clear out the system a bit. To run containers that don't keep snapshots on disk, add the rm flag when running like so. Here's a public image of a web page you can run right now on your machine. Now, while it's running, there is no way for me to access the web page. How do we solve that problem? Well, by port mapping, we can tell Docker or Podman to create a tunnel by binding a local port to the containers. Instead of doing it explicitly, let's use -P to make the system map a random local port to the one the container exposes. I'll also give it an optional name so that it's easier to address it later. We've missed one critical flag, and that's -d, making sure the container is run detached so that my local shell stays free. Podman PS shows the running containers, but now it indicates a local 5-digit random ports mapped to the container's HTTP port 80. Let's see what it holds. To print it in a more readable fashion, there's a port command followed by the container's name or ID that lists all available mappings. A quick switch to the browser at localhost and the long port reveals a web page with hello from Docker index file. To stop running a container, use the stop command with an ID or a name. Now, before moving on, let's cover the important commands so far, and again, use either Docker or Podman for both. We had ps to view running containers. We had images to view stored images. We've used pull to pull images, run to start a container in various different ways using the different flags. We used stop to stop a running process, and even mentioning container prune to clear out space consumed by old dangling containers. So we've covered backward, but before moving forward, I'd like to leave you with one present. While most terminal users, especially beginner ones, follow the CLI, and don't get me wrong, it's an excellent tool, here's a terminal user interface that can be a lifesaver. LazyDocker is an open source project, which is, by the way, sponsored by Warp, a terminal I covered on the video up here. LazyDocker pops a terminal-based interface with containers, images, logs, and all other options. It was written by Jesse Duffelt, which is slightly more known for his other impressive similar project, LazyGit, and I also got LazyGit covered in the video in the link above. Now, you've probably noticed the Docker in LazyDocker's name. If you're using Docker, skip 20 seconds forward. If you're like me, running Podman, go to the issues, scroll back to the beginning of time, and the oldest open issue in the project asks about Podman support. Inside, you'll find a rather simple line, which we'll also leave in the description, that remaps Docker host environment variable to the Podman socket path. Nushell has its own way of exporting variables, and once it's set, we can run LazyDocker with Podman processes. But before doing that, let's run a container so that we can query something. Right, with the container running, let's explore the interface. All containers are listed by default whether running or not. To filter them, hit /, I'll search for running. And here's our romantic LGML, with its logs to the right. It also mentions the image used, the volumes and networks. Moving to the images, we can see the config, involved layers, and for the sake of comparison, let's filter the BusyBox image from earlier, and here's our 1-layered 4 megabytes Linux container. With the basics out of the way, let's talk about building our own container from the ground. Here's a simple Go HTTP server. I'd like to containerize it. The widely known option for a containerization file is Dockerfile. Let's start by naming it this way and start working on building it. Every container file starts with a from line, setting the base image, the baseline for the environment, if you will. Since I'm using Go, I'll grab Golang image. That tag after the colon is the version of the built image. In my case, it's a Golang version based on Alpine, which is a light Linux distro built for containers. Workdir indicates the container path to work with, where to copy files, and where to start the process from. Then we use a copy command from the local building machine to the built container. It uses a source and a target, either a directory or a file. Then we add a run line to go build my application. I'll add an optional expose line to indicate the port my server is working with, and lastly, an instruction to run the binary built above when the container starts. All 5 lines above are build time instructions, while the last one is a runtime instruction. Right, before building, let's talk about the file. While I did name it Dockerfile to make things more conventional and less tied to Docker, you can name your file a container file, and most tooling around it will be able to work with it just like they do with Dockerfile. Now, build in a context path, in this instance dot for the local dir, starts building with the local files. You can see every step forming a layer and performing the instructions. It all ends with a commit, which is another container instruction that creates a unique hash for the container, much like Git. Running Podman images shows the recently built image on top of the list, but it doesn't have a name on it, and it weighs 339 megabytes, which isn't terrible, but not extremely light either. Let's fix both. I'll start by building again, using the -t flag for a tag. By the way, this isn't a must, since the image is already built. I can actually also run podman tag id followed by a tag. With the new some-go server tag, we can query it again using the images command. The container runs fine with no issues, but I can't query it yet. Remember why? If you said port mapping, you are right. Adding -p and the container's running PS shows the mapped ports. Now we can reach out to the API using a new port which the server responds to successfully. Now let's deal with its size. Container files have a special feature allowing them for a chain of steps. For example, we can use the first container with the Golang image as we just did, but since Golang is a compiled language resulting in a binary, there isn't a real necessity for an operating system around the artifact. So here's how pros build images. We'll add a from scratch instruction, which is a special word reserved for non-operating system containers, using the host below for anything they need. We'll then copy the product named main from the first container by mentioning its name. There are a few ways to do that. I like using the as notation and build as a name for the first container. Then back to the copy line, I'll use from builder. And that's it. Now let's build with the same name but label it as light and see whether it stands for its new name. Check this out, 7 megabytes instead of 340. Quite an improvement, but can it run? Well, it runs. Let's check out the server with the new port and voila, win. We can now query, pull, run and build containers. Now for the final touch, multi-container environments. While there are many options, one of the best is Docker Compose. Like other features, it's also available from Podman CLI, but it's a simple wrapper around Compose, so you'd want to have it installed locally. I'll use a public repo on my GitHub called Guestbook Demo App as an example. To start working with Compose, the conventional way is creating docker-compose.yaml file. I won't bore you with technicalities. The main thing to know is that Compose holds a list of containers under services. In this instance, we have 2 containers named app and Redis. While I can use the standard Redis, I'll use Valkey, which is an open source fork for Redis backed by AWS, Oracle, and even Google, and has gained immense popularity since Redis announced changes to their license. Podman Compose app will run the Compose file. Note the message above warning that this is using Docker Compose externally, which means you'd want to have the Docker engine running for this. 2 containers were created and we have both their logs printed out. I'll open up my local host with the port exposed from the Compose server, and there's the guest book that seems to be saving values to Valkey successfully. Let's kill Valky container to see what happens by running podman compose stop redis. Once stopped, the UI indicates there's an error. We can put it back up using the reverse command, compose start redis. Lastly, Ctrl+C will stop the environment and keep the containers hibernated aside. Compose BS tells us there's no environment started. I'll start it back up, this time with -d flag for a detached session. To view the logs of a detached session, run podman compose logs. To destroy the environment, compose down will tear everything down, and -v adds some verbosity to the process, telling us both containers and network aren't only stopped but also removed. Before wrapping up, compose, while great for multi-container environments, is also one great way for running development and debugging containers. Let me show you how. I'll change the compose file from building the image with every run to grabbing the pre-built image for the same service I've pushed to a public registry. The trick here is to add a mounted volume from my local directory on my laptop mapped to /app on the container, essentially sharing the same files instead of copying them. The final touch is to also overwrite the command by adding a command entry to compose, telling the container to tail -f to follow /dev/null. Now, there are a bunch of more elegant ways to make a container hold, but that's muscle memory for me. Now, compose up, both containers are alive, so it's time to learn a new command. Exec executes a command onto a container. I mostly use it to get a local shell by adding it for an interactive session and following up with sh. Now, I'm in the application container where I can start the process using go run main. It looks fine in the browser, so let's change it in real time. Now check this out. Without stopping the container, I'll open index.html on my machine and update the title. Refresh the page and what do you know, the title is updated in real time. Okay, so you're a container pro now, and you've probably seen me using Podman the entire time and speaking about Podman versus Docker. If you're interested in the why, how they differ, how they compare with each other, I have an entire video covering just that, so check this video next. Thank you for watching, and I'll see you on the next one.